We will now discuss some very simple examples based upon the two equations of the electromagnetic waves. So say you have an electromagnetic wave, and this electromagnetic wave is traveling along the x-axis. So that is, it is traveling along the unit vector I hat. And say the electric field is given to you as 6j hat. So what does 6j hat mean? 6j hat means the electric field is along the y-axis. So your propagation is along the x-axis, electric field is along the y-axis. So obviously electric field is perpendicular to the x-axis. So now what should be the magnetic field? So the magnetic field is in k hat. K hat means along the z-axis. So there is no other option for the magnetic field. It has to be perpendicular to the electric field. Electric field is in y-axis. So magnetic field could be either in the x-axis or in the z-axis. But since we are given that the direction of propagation is along the x-axis, so the only place left for the magnetic field is the z-axis. So z-axis is denoted by k hat, that is the unit vector k hat. So you can say the magnetic field is in k hat. So the relation between the electric field and the magnetic field, so this formula was written in the last slide. E is equal to B times C. Now C is the speed of light, which is a constant, 3 into 10 to the power of 8. So you know B is equal to E by C. So E is given to us 6j hat. So you have 6 divided by 3 into 10 to the power of 8, and you get 2 into 10 to the power of minus 8 k hat, that is along the z-axis, and T is for Tesla. Second example, so say the magnetic field B is given by this equation, 2 into 10 to the power minus 7 sine of 0.5 into 10 to the power of 3 x, that means it is traveling along the x-axis, minus 1.5 into 10 to the power of 11 t. So recall that our equation for magnetic field in an electromagnetic wave was given as B is equal to Bm times sine of kx minus omega t. I am writing x here because we have x here, and this shows that the direction of propagation is x. So this is k here, we have x, this is omega here. So we get k is equal to, you just plug in this value, and k is equal to 2 pi by lambda. Omega is 1.5 into 10 to the power of 11. So this is 2 pi f, our angular frequency. So you can compute lambda from this equation because you know value of 2 pi, and you can compute frequency from this equation. So lambda is wavelength and f is the frequency. Now in case this omega was not given to us and only k was given to us, we could still have computed omega, because once you know lambda, then you also know the frequency. So in the previous slide we saw that lambda times f was c, where c is the speed of light, 3 into 10 to the power of 8 meters per second. So if you know lambda, then you can compute f. If you know f, then you can compute the omega as 2 pi f. So omega is equal to 2 pi f. This you can compute. Once you can compute this, you can plug this in. Now the formula is Em is equal to Bm times C. So this value here is Bm. So you have Bm times C, and this gives you 60. So Em is 60. So now we are just plugging in the formula for the electric field of the electromagnetic wave. So that is given as E is equal to Em times sine of kx minus omega t. So we are just going to plug in k and omega from before, and you have just computed Em. Now another thing we want to talk about is, that electromagnetic wave carries energy and momentum. So the electromagnetic wave carries energy and momentum just like all other waves. So therefore, when it falls on a surface, it exerts pressure. So if it falls on some surface, it will exert pressure, and this pressure is called radiation pressure. So if the total energy transferred to the surface is, say, U in a given time t, then the magnitude of total momentum delivered to the surface, this P is the momentum, so this momentum is given as U over c. So c is the speed of light. So this is speed of light, a constant, 3 into 10 to the power of 8 meters per second. So let us see an example. This will be clear in an example. So there is a light which has energy flux of 20 watt per centimeter square, and this falls on a surface of area 2 centimeter square for 3 minutes. So the total energy falling on the surface is, so you have 20 watt per centimeter square times 2 centimeter square, and then this is 3 minutes. So this 3 minutes you are converting into seconds. So you get 7,200 joules. So that is watt times second, because centimeter square will cancel out. So this will cancel out with this. So you get 7,200 joules. So the total momentum is 7,200 divided by c, 3 into 10 to the power of 8. So you get 2.4 into 10 to the power of minus 5 kg meters per second. Now since there is momentum, that means there is force exerted on the surface. So the average force on the surface is given as, force is equal to momentum divided by time. So that is the formula. P is the momentum. I copy the momentum from here to here. So the time is 3 minutes. So this is 3 minutes. This is also given to us right here. So this gives us 1.3 into 10 to the power of minus 7 newtons is the force exerted on the surface.